Okay, so for part one of homework 4-2 here, working through hopefully the first half or so of this. So question one, they give us a force, they give us that function there, and then they define B for us, so we've got all that information to work with. How much work is done by the force moving an object from 0 to 2.6 meters? Well, again, what I want you to be comfortable with on this one, when you see the work that we're looking for here, and you've got a function representing the force, I want you to think graphically at first, right? Graphically, if I was doing force versus a change in displacement, if I was doing force versus displacement, the work would be the area underneath the curve, right? And the reason that's significant is, again, the area underneath the curve is the integral of this function, right? So to find the area underneath the curve when it's not just a linear equation, I just do the integration, right? I integrate this function. So that tells me I'm going to start with my function f equals b to the x to the third, so 3.7 x to the third, and I'm going to take that and I'm going to integrate that function with respect to x. So I'm going to take both sides and integrate it again with respect to dx, right? So in doing so, again, on the left hand side I would get the force times x, which is my work, which is exactly what I'm looking for, right? Because this would be, again, force times the integral there of dx, so I'd pull in that x. On the right hand side I'm finding the integral with respect to x. So I increase the power and then I divide by that new power. So I get 3.7 divided by 4 times x to the fourth power. And then because I do integrate it, I do have to add that plus c, right? Don't be thrown off by the plus c. So I get the work equals 3.7 divided by 4 times x to the fourth plus c. We actually don't have a way right now of finding out what the c is, but it doesn't matter because they give us two positions to work with, right? They're asking us to find how much work was done in moving it from this location to this one. So all I'm going to do is I'm going to plug into that equation and I'm going to subtract the two positions, right? So I'm going to take the way that they represent this sometimes mathematically is they're showing us we're starting at 0, we're going to 2.6. So I'm going to take 2.6 and plug that in for x, and then I'm going to take 0 and plug that in for x, and I'm going to subtract those two expressions that I get. So when I do that, I get 3.7 divided by 4, again plugging in 2.6 to the fourth power. So I'd get this when I plug in 2.6. I do still have that plus c hanging around, but I'm subtracting then 3.7 divided by 4 times 0 to the fourth power, and obviously that's just going to be 0. But then I'm also subtracting that plus c once again. So as I plug this in, right, I end up calculating this first part. This first part ends up being about 42.3. So I get 42.3 plus c minus parentheses 0 plus c. So again, whatever that constant is, doesn't matter because it cancels out. So I end up then with a net work of 42.3 joules as I go from 0 to 2.6 meters. So the big steps here that you do need to be comfortable with, to find the work, you're finding the integral, and then once you have the integral, once you have that equation, you just plug in your two positions and find the difference between the two, which again eliminates my constant from the problem. So 42.3 is what I ended up with for my N. So question 2, it says a tennis ball is bouncing off the floor 3 times. Each time it loses 22% of its energy due to heating, so it's losing it due to friction in the ground and whatnot. How high does it rise after the third bounce, and then provided it was released from 2.3 meters? So if I'm thinking about this in terms of energy, well, when I first drop it, right, it starts with potential energy due to gravity. But then they're telling me that after each bounce, it's losing 22% of its energy. Well, the way that I'm going to think about that is if it's losing 22% of its energy, doesn't that mean it's remaining at 78% of its energy, or 0.78 times whatever it originally started with? So what I'm going to do is I'm going to take my energy, and each time I'm going to multiply that by 0.78. So I know it bounces 3 times, so I would multiply that by 0.78 3 times, right? Or simply 0.78 to the third power, since I'm just doing that 3 times. The other thing that I could do, though, if I kind of pause here and think about this, I know the potential energy is mass times gravity times height. Well, no matter how many times it bounces, the mass isn't changing, and the gravity is not changing, right? The only thing that's changing is the height. So as soon as I know the energy is decreasing, that tells me that the height also has to be decreasing by the same amount. So while I could calculate the original potential energy, then calculate how much is left after each bounce, and then use the final to find my height, I could also just take my original height that I've dropped it from, multiply it by that same rate that it's decreasing by each time, right? And then that would tell me after 3 bounces my new height is whatever this number is, right? So that's all I'm going to do is I'm going to take my original height, 2.3 again times 0.78 to the third power because it's bounced 3 times. So then I just calculate that number and I end up with about 1.09 meters as the height to which that ball bounces. So hopefully not too bad to kind of work your way through this one, right? It's losing 22%, so it's only at 0.78% after each bounce. And because the only variable that changes, the height is the only variable here that's changing, right? Since the mass and the gravity are constant. So anyway, hopefully this question wasn't too bad, right, to get our way through. So question 3 here is a pretty good just comparison type question, right? They're asking us to rank the elastic potential, the spring potential energy for each of these. We know the spring potential is 1/2 k times delta x squared, right? So in looking at these, well, if I look at A and B, both A and B have the same constant and they're compressed the same amount, right? So I know the potential spring for A and the potential spring energy for B would both be the same no matter where they fall in the order because, again, they have the same constant and they have the same compression. So then the real question is, how do those two then compare with, obviously, C and D? Well, for C, right, the only thing that I change is it's still stretched by amount D, but I've also doubled the constant. So because it still has the original same distance that those two have been stretched, but I have doubled the constant, then I know that the potential energy stored in C is going to be greater, right? It's going to be greater than the potential energy stored in A and B. So I've got those three kind of in order, so then I have to throw in D, right? And potentially D could maybe fall between these as well, but let's just consider. So when I look at D, D's constant was the same, but it did double the distance it's been stretched, which, keep in mind, because I'm squaring that distance, I'm actually now making this 4 times as big, right? This would be 4D squared. So this actually ends up being 4 times as big, 4 times as great as the original A and B, whereas C was only twice as great. So finishing out the order here, the spring that stores the most energy would be D, C stores the second most, and then A and B store the same amount because they've got all the same measurements there. So anyway, hopefully not a bad question. I'm sure most of us probably did pretty well, but make sure you feel pretty comfortable on these type of ranking tasks. They do like these on the AP exams. Okay, so question 4, I told you guys I'd give you some opportunities to start to get more comfortable with these type of graphs where they're not obviously just a nice parabola to work with, but hopefully not a bad one to kind of break up here. So for part A, at what value or values of x is the particle speed at a maximum? Well, we know that the speed is going to be at a maximum when the kinetic energy is at a maximum. And the kinetic energy is going to be at a maximum when the potential energy is at its minimum, right? So the kinetic energy is going to be at its maximum when the potential energy down here is at its minimum for the whole graph. So that's going to occur at 6 meters, right? So the maximum speed is going to occur when x equals 6 meters. And that is the only location. Yes, this would have a higher speed than the areas around it, but compared with that, it's still, right, it's not moving as quickly at this location as at that one. So then hopefully not too bad on that. Part B, does this particle have any turning points? And if so, where? Right. So the thing that we do have to be comfortable with on the turning points happen when the potential energy is all of the energy, right? So anytime that the potential energy curve intersects with the total energy. So at this location right here at x equals 8 meters, and at this location here at x equals 2 meters, that's when my my object here, whatever it may be doing, that's when it would turn around, right? If I actually look from 0 to 2 meters, I never actually make it into that range because it's not possible for me to have more potential energy than I have energy, right? So this part of the graph is actually insignificant physically for us. So the turning points again are at 2 and at 8 meters. So at x equals 2 meters and at x equals 8. So I've got those to work with. So then for part C, if E is changed appropriately, so this allows me to work with E wherever I want it to be, could the particle remain at rest at any of the points in the range covered in X by the graph, and if so, where? So are there any locations at which X could remain at rest if it were to be placed at that location? And the answer is yes, right? If we take the energy and I'm allowed to adjust it wherever I want. Now, the significance of this first statement is saying that if I wanted to, I could actually make the total energy include this part up here. So we'll see that in just a moment. But the key here is it's going to remain at rest, right? It would remain at rest if it was in equilibrium and placed in equilibrium. So at any of the locations on this graph where it's in equilibrium, that's where it would remain at rest. So there are 4 locations where it could possibly be in equilibrium, either unstable or stable, but it could still be in equilibrium. And those 4 locations are the 4 minimums and maximums. So yes, we do at this location right here at x equals 1, although that would be an unstable equilibrium, as any type of disturbance would cause it to move, right? It could be placed there at equilibrium and it would remain at rest unless something happened to it, right? It could happen at x equals 4 as well. And then finally, my stable equilibriums would occur at x equals 3 and x equals 6, right? The minimums are the ones that are stable because it takes a much greater disturbance to cause those to break free from their equilibrium, or at least not as easily deter from that spot, right? So anyway, these are the 4 locations for which the object could remain at equilibrium. So make sure you are getting pretty comfortable interpreting these graphs. So then question 5, probably the last question or so we'll get in on this first part. But a 5 kilogram mass hanging from a spring scale is slowly lowered. The scale reads in newtons. What does the spring scale read just before the mass touches the spring? Well, before the mass touches the spring, the only forces acting on it are the scale and the force of gravity, right? And since, even though it's being slowly lowered, since it's not accelerating upward or downward, we know that those 2 forces would be equal and opposite. So the scale, which I'll maybe call that SC just to distinguish that in a minute here. But the scale force would be, again, equal to the force of gravity. Well, in this case, the force of gravity would just be my 5 kilograms times 9.8. Using our 5 rule, of course, that's just 49. Right? So I know the scale force would be 49 newtons before it interacts with the spring. Once the block begins to interact with the spring, now the spring is, as the spring compresses, right, the spring is also going to push upward as well. So once the interaction begins to occur, I've got my mass, and then I have both the scale force, which again I'll call SC, and then the spring force, which would be pushing upward, and the force of gravity would still be pushing downward. Right? So those 2 forces, both the spring and the scale force, are working together now to balance out gravity. So when the scale reads 20 newtons, where the lower spring has been compressed by 2 centimeters, what is the value for the spring constant? Well, again, the key concept here is I know collectively these equal the force of gravity. So my scale force plus my spring force equals my force of gravity, which is 49. So my scale force, which they told me is 20 newtons in part B, and then my spring force, which I would calculate by K times delta X, well, the delta X has been compressed 2 centimeters, right? So 0.02 meters, and then that needs to equal 49. So once we've set this up, not too bad to solve it, right? Just subtract 20 from both sides. We get K times 0.02 equals 29, and then dividing both sides by 0.02, I get K to be about 1450 newtons per meter, right? And keep in mind the units are very important there. We want to make sure we're comfortable with those. So it is newtons per meter. Anyway, we've got that for part B. And then finally for part C, at what compression will the scale read 0? Well, hopefully that's also pretty straightforward, right? The scale, the spring scale here is going to read 0 when the spring beneath it is supporting all of the weight due to gravity. So the scale force would read 0, right, when the spring force is pushing up enough to balance out the force of gravity. So now I need my spring force to equal the force of gravity. Well, the good news is I just found K, so whatever that constant was, I'm going to use that again. So it's 1450. I don't know the compression, that's what I'm looking for, but I still know my force of gravity is 49. So solving for delta X, right, solving for X there, I end up getting about 0.034 meters, or in other words, about 3.4 centimeters. Right. So anyway, either of those answers obviously is fine. 3.4 centimeters, not meters. But hopefully you are pretty comfortable with this type of question. So I'll go ahead and stop part 1 of this video here. We'll pick up questions 6 through 9 in the remaining part.